This is the physics talk. Before I get started, I actually wanted to quick show, because I wholeheartedly agree with Lucas that you should use autocomplete, and we actually hacked the functionality of Flash Develop to parse the Unity JavaScript. So we actually code in JavaScript, which is pretty alien to a lot of the other more established people. So this is a JavaScript, but we have full autocomplete. Let me see if I can zoom in here. So we have full autocomplete parsed from the doc, so we actually get like little doc snippets. And then it's both for the Unity stuff and then for our own script. So in the project, there's a Minotaur script, and then all of our stuff is on there. It has the same problems as Flash or Visual Studio in that it's a Windows-only solution. So you're also stuck with a two-box solution or a VMware sort of thing. We are going to release this probably next month. So if you're interested in getting it, please remind me to actually get off my ass and release it. But on to the actual talk. So this talk, who here was at my talk last year at the first Unite? A couple people. So that was more of an abstract talk. The video is still online on the website if you want to check it out. This talk is going to be a lot more practical. Rather than talking about how I think about physics, it'll be here's the stuff that we encountered, here's the stuff that we've done, and here's how we've actually done it. So again, it's just I'll go through a really quick intro. I won't spend too long on that, and then I'm just going to launch into a bunch of the different stuff that we've done on our projects. So I am the founder and CEO of Flashbang, and then I'm some other stuff. So just in the logos, Steve and I also run the Independent Games Festival and the Independent Games Summit held at the Game Developers Conference. If you have any questions on the IGF, just find me during the show. I also run a website called Funmotion, which talks exclusively about physics games. And those are games like Bridge Builder, Armadillo Run, Gish, games that are based very, very heavily on physics. I'm a unicyclist. I like to throw that up there. But the thing that takes most of my time is Flashbang, and we are a 6-person team. All of us are here. So here's some of the games that we've worked on with Unity. This is actually a Unity 1.6 project for the 3DU contest a year and a half ago. And it's basically a ragdoll game. The game is you throw metal pies at ragdoll clowns, and there's a sort of simple scoring system. You get more points if you hit them while they're in the air. We're actually going to put this on the iPhone pretty soon here. Our second Unity game was actually made for the Unity, back then it was the Top Dog contest, but for the Unity Awards last year. It's basically a puzzle bobble, bust-a-move game, but based on physics rather than based on a hex grid. And this was made in about 4 weeks for the first version, and I think 6 weeks total, with 3 people. Then we followed up with Off-Road Velociraptor Safari, a game in which you are a velociraptor hunting other velociraptors to kill them and teleport their meat to the future. So this was basically a test for us of the terrain system and then a test of vehicle physics. And we recently launched Jetpack Brontosaurus. You saw some of the visuals earlier. I want to talk a little bit about like the ragdoll technology that we're using. And then our next game, which should be released in November, is a game where you're a Minotaur running a China shop, serving customers who come in, ask for a certain teacup or a plate. But you're fresh out of the labyrinth, serving a prison sentence for destroying China shops. But this time around, you've actually purchased rage insurance. So as you're playing, he's actually a ragdoll the entire time, which is why he walks a little weird. So if you start to trash the place, you might as well utilize your rage insurance, sort of start really destroying things and getting payouts from your insurance. It's a pretty simple game in terms of gameplay, and it gets a little extreme at the end. And then, of course, if you start making too much money off your insurance fraud, security comes and they fire arrows at you until you're subdued for the day. And then tomorrow, for some reason, you're allowed back in the store to do it all over again. So this is when the ragdoll starts to become a little bit depowered. You can see that as the joint forces go down, he basically collapses. So all these games are up on our new website, Blurst. It is basically a portal for Unity games. We are looking at licensing some content sometime in 2009. So if you have a Unity content designed for the web that you think is quirky and interesting, find any of us. We're wearing these Blurst hoodies. We're pretty easy to find. So that is the intro. And as you can tell from all of our games, we really love physics. That's kind of a personal fascination of mine, and I kind of force it on the company. So of those games, we basically did ragdoll physics. We did a lot of stuff with joints. We did some 2D physics, sort of pseudo 2D with the 3D physics stuff. And then we had basically active ragdolls. Like they're ragdolls all the time, even when they look like they're walking. It's worth noting that I don't like doing tech. I don't want to actually roll my own physics engine. The guy here with the white hair does all the hard work, although it's actually more like that. Back when he had luxurious long hair. So that begs a quick question of, why focus so heavily on physics? And I think the easy answer there is that we actually get a lot of stuff for free out of making heavy use of physics. Although this is the dollar, so let me do the currency conversion there. So some of the benefits, and I won't talk too long about this because, again, it'll fall back into a larger abstract talk, but when you use physics, you get a very intuitive possibility space. You don't have to explain to a player that if you throw a ball and it hits the wall, it's going to bounce off the wall, but you might have to explain to the player that if you have a pikeman fortified in a city and this unit attacks, then this is actually going to happen, even if it's not super intuitive. Like, how did the pikeman just destroy my tank? But if you deal exclusively in physics, then everything sort of makes sense to the player. Everybody understands how gravity works, how collision is supposed to work. And then even the same game again and again and again can become very enjoyable because it'll happen a little bit differently every time. The number one Raptor Safari player has played about 2,100 games. At 4 minutes a game, that's 160 hours. So the replayability there is very, very enjoyable to some people. And I'm on a quick rant about consistency, because I think this is the biggest benefit, and this is actually the experiment we're doing with China Shop. So to look at it from a visual analogy, this may or may not be an iPhone game where you fly a helicopter picking up Raptor ragdolls. So because the iPhone is a limited visual platform, we've had to do some things here where we've kind of gone back to an older graphics technique of parallax backgrounds. So it looks great from this purpose-built presentation format, but it limits us. Like, let's say we wanted to have a camera angle from the cockpit of the helicopter, or move the camera in and then orbit it towards your velocity direction. And of course, because the parallax backgrounds are sort of a visual trick, if you see both the scene view and the game view, you suddenly realize that we can't really move the camera at all. We're stuck in this really weird perspective. Well, it's not weird, but we basically can't do anything where we would orbit the camera more freely. So in a visual way, this is extremely, it's not consistent. It's purpose-built for one goal in mind, rather than taking a very general 3D world and making it look 2D simply because the camera is looking at it 2D. So from a gameplay angle, I have a gameplay after this. So in a specific, you basically create something for the interaction you have in mind. And in a general solution, which is what we try to do with our physics stuff, the code that's there is actually a simulation code, and you layer your gameplay on top of it. So again, it's basically purpose-built versus you're covering all scenarios, and then you're narrowing that possibility space down to just vehicle physics, just a character ragdoll. So the point I'm making about cohesion and why we focus on it is that if you do something specifically, it's very difficult to move up to stuff you might not have considered while you were creating it. Like in the parallax visual example, it's very difficult to make it 3D visual. Where in the general solution, you're going to start with a simulation and then narrow it down to what you want. So the gameplay example is Adventures of Lola, which is a block pushing game. You basically push blocks around. And this is specifically built because it's an older game, but also because it's sort of a puzzle game. But because there's not an underlying simulation there, you couldn't easily do things like, let's have a level where the board is kind of tilted one way or tilted the other way, or magnets, or some blocks are really heavy, or you can spray it down with ice and the friction level goes down. All those things aren't possible without coding it. So to get onto the practical stuff, let me talk about a little bit of basically all the videos that you saw. I'm going to try to cover the core tech from each of those games as quickly as I can. So I apologize if this is pretty quick or fast, but we will be posting a lot of these snippets to our website and to the wiki. So I'm going to start with vehicle physics. Zoom in a little bit so you can see the intent look on his face. So here's Raptor Safari running with all the debug information shown. And it is important to get debug information while you're testing the game so you can sort of correlate in your mind when you're tuning numbers, what does a friction value of 10, how does it behave compared to a friction value of 20? Watch the wheels on the car as he goes over these little ruts. You'll see how they're actually snapping up and down. And I'll talk about why that is later. But when we were designing Raptor Safari, we had a lot. The actual design from the get-go was you basically hunt raptors and you tow them around in your Jeep. So from a physical point of view, we wanted extremely robust physics that wouldn't explode at high speeds, wouldn't explode if you rammed into a ragdoll. So it's actually a fairly stressful situation in terms of what we were trying to do with the physics system. So just to go through the requirements as we were thinking about how are we going to implement our vehicle physics, the first one was that it had to be stable. A lot of the shortcuts that are taken in physics implementations produce numerical instability. If you have like a 20 or 30 long segment of a joint, it might start to explode, it might start to jitter. And we did want fast speeds, we did want a lot of ragdoll collisions. We wanted to be able to tow things around, so we had to make sure that whatever we implemented was stable when players were doing these really, firing the boost and ramming into 3 ragdolls or trying to tow 4 things at once. We did want it to be tunable. We wanted to be able to change variables to get a very specific feel. While I was tuning the game, I actually wanted to enable certain actions, such as two-wheeling the car up on 2 wheels. So we had to make sure that we had enough visibility into the actual numbers that were going on so that we could tune it so that these things were actually possible. I spent a lot of time two-wheeling when I was in the start of the game. And then we also wanted this exaggerated writing ability. If you go back to the video here, let me jump ahead to when I'm falling. You'll notice that even when you jump off pretty much any cliff, it's extremely rare that the vehicle will actually stop or even land up. It pretty much always springs to its feet like that, but it doesn't look like you land on your back and then the game immediately flips you. It just sort of happens that you almost always land on your feet. Now, that's basically a really low center of gravity. We also adjust the center of gravity as you connect to something, and it actually gets even lower. So if you have a Raptor connected to the Jeep, the center of gravity is actually probably 3 or 4 car lengths below you. And if you do a barrel roll in the air, you'll actually see that. It looks like you're orbiting a point in space that's not in the middle of the car. And there's some two-wheeling that we wanted to be able to tune it so that two-wheeling was a skill. It wasn't this random thing. Let me jump ahead again. And then finally, we wanted a solution that was transparent. So we actually understood mathematically how it was working. And that makes it easier to tune things, and it also makes it easier to debug problems. And it makes it easier to use it again. So we have this base of vehicle physics that we can go back to if you want to make like a car combat game or something. So the options that we considered when we started to research it, the first was what I basically call a ragdoll car. This is where the actual parts of the car are individual rigid bodies, individual colliders, and then the wheels are actually connected to the body with a joint, a character joint, a configurable joint, a hinge joint. And you're actually applying torque to the wheels to actually move the car forward. So you're basically relying on the entire physics system to simulate exactly what you would want. So the pros to this are that everything is built in. You don't need to write very much code. You can just sort of connect all the components within Unity. It's very easy to visualize, and it's very intuitive to think about. If you wanted to build an A-frame suspension where the wheels would squish down, you basically just model an A-frame and have the joint set up so that it works properly. And actually the biggest pro here, and pretty much the only reason to actually consider it, is that it's really easy to do arbitrary designs. If you wanted to have a car that was 6 segments and kind of a snake, and each segment had its own 2 wheels, you basically just model that, connect it together, and then hopefully it works without exploding. But as I sort of alluded to there are a huge number of cons to doing this. One is that the physics system is not intended to simulate angular velocities above a certain speed. There's actually a limit by default on that. So your tires don't go very fast. It doesn't make sense to have wheels that are spinning at like 10,000, 20,000 RPM. The joints in themselves will start to explode, especially if you're ramming things. Then you basically end up with a really, really big mess. So we tried that actually, and then we ruled it out pretty quickly. The other option is to use the PhysX component. It's basically native to PhysX, is the wheel collider. And the wheel collider doesn't use the same friction calculation that anything in the actual like 2 boxes might when they collide. It has its own friction calculation that's actually pretty similar to the one that we ended up using, but the car body is still defined by colliders. You usually just have one rigid body, unless you maybe have like a tow truck scenario that has a hinge on the back of it. So the pros here are that, again, it's just built-in components, and then you can hopefully assume that it's a very fast solution because it's implemented at the engine level by PhysX itself, not even by Unity. They're basically just exposing what's already there in the SDK. But if you look on the forums for wheel collider searches, you'll find out that a lot of people are very confused about how it works, what values you should even be using. Like if your car has a mass of 100 and you're expecting speeds of this, what do you set for any of the values? There aren't really any good examples, and because it is this component that's built into PhysX, even behind the Unity layer, it's not very transparent and it's not very extensible. So we looked at that, couldn't really get a good solution that felt good, and then ruled it out. So the final solution, and the one that we used, is basically a raycast car. This is where everything is modeled from scratch. You sort of have to decide, if my car is supposed to be going this quick, this fast, and it's going this fast instead, what forces do I apply to the car to make it rectify between the actual simulation and what I want it to be simulating? So this is actually a hovercraft car. You have one rigid body. It's defined by multiple colliders. And the wheels are actually not, they're there to visualize how fast the car is moving. So the actual wheel rotation is just arbitrary. It's just to show you, the player, how fast the car is actually going. And the wheel rotation is just to visualize which way the rays are actually going to be applied. So just to break it down here, it's very transparent and very extensible because it's basically a script-driven solution. And then if you have one rigid body, you basically have a lot more stability options in mind. You don't have to tweak multiple values. You basically tweak the one rigid body. And if you script it well, it is easy to rig new vehicles. It's really easy to actually keep using this code again and again. And of course, the cons, the wheels have no collision. They're basically moving to whatever the rays are hitting, and that's why the wheels were snapping in that video. As the rays passed over an object, suddenly the ray was a meter higher than it was the previous frame. And we actually smoothed it out a little bit in code, but the actual wheel contact point isn't round. It's just a single ray point. You do have to code it from scratch, and then the more technical aptitude you have, the better you are with scripting, and the more comfortable you are with mathematical concepts, the easier this will be. So the starting point for you guys will hopefully be us, but we actually based the Raptor Safari vehicle logic off Forrest Johnson's code. He's Yagi on the forums. We had to adapt it to our coding style, specifically the coding style of commenting, which he did not do. But we're going to release this car tutorial on the Unity resources section, both the car projects you will see later and then a PDF. But even then, it just takes a while to fully comprehend what's actually going on. So let me walk you through it. This is the vehicle in Raptor Safari, and this is just the wireframe view of all the colliders. You can see that we have individual colliders for the doors, and that's what if you hit those colliders, even though you're hitting the same rigid body, you actually can ask which individual collider did I hit, and that's what we use to break apart the doors, to break apart the rear there will actually swing open. So when the rear is closed, it's actually not a rigid body, and then when you open it up, we make it a rigid body, add a joint to it, and then the back flaps open. So here's the implementation. I'll just walk you through it rather than say it and then say it again. So here's the car from the car tutorial project. So the first thing in our implementation of the raycast vehicle physics is that we're internally modeling the engine speed. We don't just look at the rigid body velocity and assume that's the engine speed. So when you hit up and down on the keyboard, the engine speed goes up. And over time, there's like a friction value applied. So the engine speed, if left alone, will drift towards 0. And these are actually pushed to individual wheel speeds. And again, when I say speed here, I'm not talking about the actual velocity of the wheels. It's an internally modeled, this is how fast this wheel is spinning. And in our model, we actually do not track the wheel speed individually. There's an individual value, but it's basically pushed from the engine. You could track it individually, so if you wanted the front wheels to be off the ground and spinning in the air, but the rear wheels to not have the speed. And one of the benefits of tracking the speed independently is that it just makes more sense. So if you're in the air and you're jumping, you can still rev the engine, speed up the wheels, and then when you hit the ground, you're going to have a bunch of wheel momentum built up. So the raycast car we defined 4 points at the top of each of the wheel wells, and we fire rays downwards from this point. And the rays have a maximum distance that they'll go, and that's basically the maximum distance of the wheel. If the ray doesn't hit anything, we assume the wheel is in the air, and then we basically move the wheel to its bottommost point. So if the ray does hit something, like let's say it only goes a little bit and then it hits ground, we can assume that we should model some sort of suspension force out of it. So this force goes up the shorter the ray gets. So if the ray only travels, actually I think I have a pointer on here. Yes. So if the ray only travels right there, we can assume that the tire is compressed, and this suspension force will actually go up. And that's basically the gist of this suspension force, is that the shorter the ray goes, the more force it gets pushed up into the car. There's also a dampening force to prevent if the car is tilted one way, we push up an equal and opposite force, then we're going to get tilted exactly the opposite the other way, and then your car just kind of oscillates back and forth. But if you dampen it in a fixed direction backwards from the actual force going upwards, then you end up sort of, if you're here, you end up a little bit over and a little bit less, and then you're finally stable. And these numbers are all tweakable separately per wheel. So you could model a car that had wheels in the front that were very stiff, or wheels in the back that were very stiff. This is actually probably a bad car design for the tutorial, because it's tuned even to be very stiff, where you might want like sort of a buggy. So that's the suspension force in the wheel. Does anyone have any questions on that specifically before I move on? And if you think about it, it's actually a hover car. We do move the graphical wheel to match the contact point so you can see where the wheel is colliding, but you can just throw away the wheels and get a hover car out of it, and it's basically modeled the same. And if you wanted to, you actually can increase or decrease the wheel contact points. So if you wanted 6 wheels, or if you were just doing a hovercraft, you might just want 8 points of contact and no wheels at all. So the actual forces, so let's pretend our car is doing sort of he's turning to the left and he's swinging out to the right in sort of a drift turn, like his ass is coming this way and he's turning around this way. So the actual velocity of the car is this green arrow on the right, where the car is going this way, but there's actually a little bit of body rotation. So what we do per wheel is there's actually a function to ask our rigid body, what is your velocity at this particular point in space? And what that's doing is it's applying the rotation into that number. So even if the body is going this way, but it's really rotating out, you can say, well, what's the point? What's your world velocity right there in the rear? And that'll actually be more towards the direction of the rotation. So we take this world transform, or the world velocity at this point, and we do an inverse transform to put it into the local space of our wheel. So then we can very easily model, the blue arrow this is the actual velocity at this point on the car, basically the velocity of the wheel. So you say, well, the wheel's going this way, it's going forwards in the wheel's transform space, coordinate space. It's mostly going forward and a little bit to the side. So what we do is we look at the actual speed, like the internal speed of the wheel. So if the speed of the wheel is less than or greater than, then we'll actually apply a force to fix that. So if the internal wheel speed is like 20 miles an hour or 1,000 kilometers an hour, whatever the conversion there is, if it's 20 miles an hour but the wheel speed is 30 miles an hour, the wheel wants to apply a force to the car to make it go from 20 miles an hour to 30 miles an hour. So this actually might be the difference there, and I actually have those arrows reversed. So imagine the lighter blue is your actual car speed, and the heavy blue is the wheel's internal speed. It's going to try to apply a force to rectify that, so that its internal speed will begin to match the actual real-world speed. And we do a split here on, we model this differently for forwards angles or forwards motion and then sideways motion. So the reason you model it differently is you can say it's very easy for the wheels to apply forces forwards, which makes sense because it's spinning forwards, and there's a lot of friction sideways. So there's the key functions that make this happen, but I went backwards. So that's the gist of it, and the key in the implementation is that you model friction differently. So the sideways friction is very, very stiff. So if the car is coincidentally drifting sideways, it'll come to a stop very, very quickly. And if it's mostly going forwards, it'll be able to go forwards very easily. And if it's going some combination of the two, where it's kind of drifting sideways, it'll prefer to go forwards versus continue drifting sideways. And I should have put a graph in there for the friction model, but the friction model, this is the same as the wheel collider. It's actually sort of a bell curve, where if the wheel wants to go 30 miles an hour, but the car is going 20 miles an hour, you might have a lot of friction. But if the wheel wants to go 100 miles an hour, but the car is going 20 miles an hour, you actually want to model it slipping. If you imagine just a car the wheels are going very, very, very quickly, and then it hits the ground, it's not going to catch immediately. It's basically going to spin out. And one thing that we didn't do in Raptor Safari, but you would probably want to do in a more vehicle-focused game, is model those values differently. So if you're over ice, you could say there's almost no friction applied. Like, it's really difficult for you to get traction on this. And then if you're over some sort of heavier ground, you would actually model it differently. So it'd be really easy to have the ray tell you what object it hit and then have some sort of property on that object. Are there any questions on how we've modeled vehicle physics? Yes? It, it emerged from the formulas for us. So we basically have a slip threshold value. We basically started with force numbers, which were, he takes the exponential of it. So it starts to slip very, very quickly, but for the most part, you're in this bottom of the curve where you're not slipping. And then as you approach the slip threshold, it just, at some point, you lose all friction if you're above a certain speed. No, we basically just kept it and just tuned his numbers. I mean, we didn't really change his model very much. This is the model that he had come up with. But it's a very common model if you research how to do real-time car physics. Any other questions on the vehicle stuff? We'll be releasing the project sample, which is basically this car in a little environment, and the scripts are cleaned up, and there's no references to Raptors in them. So as I mentioned here, yeah, don't worry too much about the details. I just wanted to cover how we approached doing it. And I would do it the same way again. It's very convenient to do all of your own scripts, and it's really not a whole lot of code. You could just sort of model the internal speed, and if you think about it as the goal of the wheels are to take whatever speed they want to be at and apply forces back onto their rigid body, say speed up, I'm not going fast enough, or slow down, I'm going too fast, then you basically have modeled everything. And it's just a question of balancing the numbers. So 2D physics, but first an intermission. I thought so. What time is it? Things. So 2D physics, I will quickly cover how we limited things to 2D. And the reasons for doing it are things are much, much, much simpler in 2D. Especially if you're trying to make a game mechanic based on physical interaction, you just want to get rid of the third dimension. So the simplest solution is actually to model it as you would an ant farm. You just place two really big cubes around your play space, and then if objects in that play space are about as wide as the ant farm, they probably won't be able to rotate. They'll maybe jiggle back and forth. But the problem is you can't have different sizes. If you want something that's wider than your ant farm, then it can't fit inside it. But it's still a more intuitive solution. And the other solution is actually to use configurable joint, which I'll talk a bit about in the next 5 minutes or so. And with configurable joint, you can actually put it to configured in world space, and with the settings here, you can lock it down for 2 motions, or you basically keep it free for maybe X and Y, lock it down for Z, and then enable only angular on Z. So let me show you what this looks like. I can open up Unity. And this actually works extremely well. And you can place multiple joints on an object. So in Sploom, for instance, we had a configurable joint on every object to limit it to 2D, and then we had a configurable joint, some sort of rig between objects as well. Still opening. And 2D in general is much easier to do faster paced things. Like if you wanted to do a physics-based 2D platformer, it'd be a lot easier than a physics-based 3D platformer. And it's a lot easier to do upright forces and things. Jetpack Brontosaurus open, which likes to take forever to open. Your other options for 2D physics are to maybe, you could probably port Box 2D to Unity script itself, or you could maybe just roll your own. But it's not too difficult to limit the 3D physics stuff to 2D. And the problems with both of them are, both these solutions, if there's enough force, your objects basically, the joints begin to pop out, and then maybe one gets pushed out of the 2D plane and is constantly trying to fight its way back in. Sleepy asset server timed out. So here's the ant farm solution, just to real quick see what's going on. We have here just two big cubes, and there's a little sliver between them. and then objects can exist in this space. They don't really get pushed out, but you can see there that they jitter a little bit as they really start. The ones up there had been falling for quite some time. It's actually slower in doing this test. I wouldn't recommend AntFarm for this physics system. But the joint solution is actually pretty robust. And you'll see here the same problems as these things have been falling for a very long time. They have a ton of force. They'll actually, like these two, manage to completely pop out. And here's the really weird visual artifact from, I guess it's the integrated graphics. It's like a weird circle. I don't get it. So here's just a 2D system, some gizmos on. And it's really easy to model which objects are in contact. And the fun thing about 2D physics are, now that you're basically doing a 2D board game, but with physics, you get all this emergent behavior. If you change the friction values, you can actually make it so they have a more tendency to fill in the gaps like that, or they have less of a tendency. So I mean, I would encourage people to look at doing physics for even things like a 2D puzzle game, like if this were a color matching game where you clicked on clusters of color. So that's locking things down to 2D. We'll release this as well, so if you want to see exactly, but it's basically those four settings. Oops, I already showed it. So to talk a little bit more about configurable joint, it's actually an amazingly useful tool in any kind of physics setup. So there's basically two modes, and it's not very obvious that there are different modes and different ways of thinking because it's just a checkbox, or tick box, as apparently you like to say. So there's a checkbox at the very bottom called configured in world space. And if you're configured in world space, you can think of it as a global constraint. You can say you can move inside this little space. Maybe you can move from -10 to 10 on Z, but that's it. And it's really good for mimicry, where you can basically say you want to match the orientation of some other object. So in the helicopter game example that I showed for the visual stuff, we were actually using a configurable joint to say, try to match this world orientation. So as you tilt the iPhone, it'll actually tilt the actual object. And then local space is basically for any sort of ragdoll joint. You want to say you can only move from here to here, but relative to this top object, even if the top object is moving somewhere else. So to talk briefly about using configurable joint for mixing physical and non-physical objects. So the immediate option available in Unity is to make your rigid body kinematic. And that means that it will still send collisions, objects will still collide with it, but it will not receive collisions. If you tell your kinematic body to keep moving forward and it goes through a static collider, it will just keep going through that collider. So the problem there is, for instance, in the iPhone helicopter game, if we made that a kinematic rigid body, we would have to start sending rays out from it to see if it's going to collide with the ground to stop its rotation. But the easier thing to do is just to make it a rigid body with a configurable joint, trying to match that orientation, but still within the actual physics simulation completely. So if it's colliding with something, it'll still apply a force to try to get there, but it's not just going to penetrate that object without us checking for it. So you saw it quite a bit, actually, in China Shop and even in Jetpack Brontosaurus. But if you just use configurable joints and you constantly update their target rotation, you can basically have their target rotations match actual animation data. And the best way to think about this is to think about them as muscles. You say your target rotation is maybe this angle up here, but you can only apply so much force to get there. You can only apply, and then apply dampening to it. So rather than just applying an arbitrary torque, you can sort of think of it as a muscular force. It's not quite the same, but it's good enough to think about it that way. And other joint uses that I'll show you a little bit is you can also do it as a way to keep objects upright. If you say you're a rigid body and you say you're jointed to this object, which is always going to be pointing upwards, and you have so much force to sort of upright yourself to that. That's actually how we keep the Minotaur from falling over, but I'll show you that in a second. So to segue from mimicry to physical characters, the simplest physical character is the ragdoll. It's a very, very old technology now. It's been around probably since, I think Hitman was the first game that really had some advanced ragdolls. They're very easy to create. There's actually a creation wizard within Unity scripts. I think it's in standard assets to make a ragdoll. But the problem is they're difficult to control. If you have something enter ragdoll and you want to move it around as part of your gameplay, then do you just drag it around? How do you make them upright? It's very difficult. And when you transition to ragdoll, it's very hard to get out of ragdoll again. Like if you have a character enter ragdoll and collapse on the ground, then how do you transition to some sort of stand-up animation? How do you go back to anything that's not just completely physically controlled? The one thing that we do in Raptor Safari is we track, even while they're animated, we track the velocities of each of the parts. So when you enter ragdoll, if the raptor is running a certain way, it won't look like he is just kind of transformed and collapsed. We basically apply the forces that are from the animation data back onto the ragdoll so that the ragdoll's initial movement matches what his animation was. And that makes it very, very easy to have a death animation that is ragdoll driven but doesn't immediately just crumple and snap. It can actually be thrown. So the answer we found, and what we experimented with in Jetpack Brontosaurus and did much more in China Shop, is that this character is actually a ragdoll all of the time. So you can see that some joints are much more matched to animation. I just entered ragdoll with the debug key. And then when I let go of the debug key, he kind of snaps back into it. So with this system, we're actually mimicking an animation data. I'll show you a live demo of this later. But our system, we can say for this individual pose, we want these objects to be so strong. So when I kind of hover off the ground, he snaps into a pose where his legs are ready for landing. And as I get higher up, he transitions to a different animation where he's kind of swimming in the air. And for any of these animations, we're actually keeping his tail with a very weak joint strength. So his tail will kind of flop around no matter what pose he's in. So if I go back to ragdoll here, and what's funny about this, he has this tendency just to fall with his feet upwards like that, just because of the way the masses are distributed. Oh dear God. So the target rotation matching stuff is the key for all of this, and it turns out that it's actually really simple. So we have a ragdoll rig with configurable joints, and then every frame we're updating that to match the rotation of some animation data. So the setup on it is we basically, we have some sort of ragdoll script, and we attach this controller script to it, and we say, controller, match the animation data of this other rig here, which is traditionally animated, it's not physical. And then we have some functionality to set the strength so that we can kind of stun creatures and whatnot. And then in the setup period, we basically iterate through all the configurable joints in the ragdoll rig and figure out what's the matching pair in the other rig based on name. What has the same name as us but relative to the other parent. And then the script just matches rotation. And this is the actual code. Like, this will match rotation. So all it does is record the initial rotation, because in configurable joint, target rotation is relative to the initial transform of the object. So if the object is already here and your target rotation is 0, it'll be whatever it was when it started. So you basically just do a little bit of quaternion math, which is always dark magic to me. And then you end up with the target rotation of the joint matching the actual rotation of our target object. This is all we do to match Jetpack Brontosaurus and to match Minotaur China Shop. So let me give you an example from Minotaur China Shop. And in solving these problems, it turns out that it's really, really difficult to get a character that's physically cohesive at all times to walk without looking like a goon. But we really wanted to try to stay 100% physically cohesive for this project. The better solution is stuff like the Euphoria, like the stuff that you see in Grand Theft Auto 4, but that's actually using neural networks to train objects on how they can actually physically walk, and that's way above our sort of pay grade. So as soon as the asset server times out, let me give you an example. So here I've exposed two of the values. Two of the values here. So this is actually visible now. So this white untextured object is the actual animation rig that we are matching. And you can see even with the default values, when I do a swing, his arm kind of lags a little bit behind. And then we're using a kinematic rigid body that matches the rotation of the animation target's pelvis. And this actually proved to be a little bit challenging because there's no relative rotation available. It's the root object of another rig. So we actually look at what it did last frame in its rotation and then match it. So we can match its rotation without having any point of reference. So there's one, this top one is actually the pin that's holding him upright. So if I drag that completely off and try to walk, there's actually no upright force anymore. So this is what happens. He just ends up kind of walking on the air. And the interesting thing is, with the pelvis matching the rotation. Oh, I don't know how to get those buttons out of the way. There we go. With this pelvis matching rotation, we don't actually need to apply any cheat forces. If we turn this up, the actual force that's locomoting him forward and backward is his feet and the friction on the floor. So the other slider is the global joint strength for his entire rig. So if I pull this to about halfway and then do a swing, you'll see there's much, much more lag. And when I start to walk, he gets a little bit clumsy. And then if I drag it even further down, you'll see that he no longer has tons of joint force. If I do a swing, it's incredibly laggy. And he's basically, like, the forces available to the configurable joints to match the rotation are very, very weak. So yeah, this is what we do when he gets stunned, is that you can end up with a bunch of arrows in you and sort of climbing around. And of course, the problem here is his actual center of gravity is draped forwards. And if I turn the pin down as well, then you end up with this really dismal-looking creature. And if I drag the sliders all the way down, he basically ends up as a ragdoll. And then if you just turn him back up, if you turn his force back up and the pin force back up, then he's back to the way he was. And that's why he walks a little weird, is that we haven't yet fixed the collision on his hooves. But you can basically go into ragdoll and then back out of ragdoll. And it doesn't look like he's standing up. It looks like he's a crazy puppet, but it's good enough. So we'll be there's actually not much to it, but we will release a sample project just showing how to actually put this all together. But that's the core code that does it. It's actually a very tricky use of configurable joint, but it's very, very easy. So I'll talk real quick on tuning these things. So the first tip, and John had a great talk about editor windows, but we use a lot of editor windows for tuning purposes. So when we're actually trying to get the mass distribution correct and the dampening correct and the joint forces correct for default values, all we really care about are like the mass of an object and then maybe 2 values on a configurable joint, and it's a real pain to walk a hierarchy just to change those 3 values. But it's also really simple to make an editor script that just gets all the configurable joints in a hierarchy and then gives you all the options available. And we can have buttons up top for making them all go up by 10%, all down by 10%, just these individual values, and we're putting out a ratio of the joint strength to I think, joint strength to joint dampening. So make tools. It's really easy to do with the editor windows, and it's quite excellent in terms of a time saver. Also save versions of your project at different points so you know what it is that it's really easy just to tune a good feeling into a crappy feeling and forget that 4 days ago it actually felt a lot better, it was a lot faster. And then just know what you're after, and then just practice tuning a ragdoll, practice doing something else. Let's talk a little bit about how to make rigs stable. Actually, before I go to that, any questions on the character mimicry stuff that we're doing? No, it's using all the physical stuff. So as long as you have enough juice available to keep your time step going, then it should be okay. Yes. No, we haven't actually used that. I looked at it, but it was very complex. So we actually, when we were doing Jetpack Brontosaurus, we had actually been using character joint and not configurable joint. So we created scripts that would take a character joint-based rig and convert them to configurable joints. And we also have some scripts that'll copy configurable joints from one hierarchy to another. But those scripts are basically, they were very purpose-written, and they would be ugly. They would probably waste time if we put them out there versus save time. But yeah, it would be nice to have a very big stable. We have some scripts that do things like adjust dampening for an entire hierarchy. So if like this ragdoll rig is way too jittery, you can just, with one click, increase the dampening for all of its values. And it's probably 2 or 3 hours at this point. It's basically to rig, like we had to re-rig the Minotaur when we just decided to change scale and some other stuff. And it basically kills a day from start to finish, including rigging and then tuning and adjusting and tweaking things. So stabilizing, again, the real problem is all the shortcuts taken in a real-time physics engine produce a lot of problems. So the first thing to look at are actually the global sliders. By default, Unity's physics runs at 50 hertz, so every 0.02 0.02 seconds, it'll run an actual update. And you'll probably want to decrease this if you can, or maybe increase it if you're having problems with small objects going through other objects. And the default values in the physics manager include things like the minimum velocity at which a body will go to sleep, the maximum angular velocities, and the solver iteration counts. You should tweak with these. You should try to lower the solver iteration count or increase it if you're having problems. And to make things more stable, you usually want to increase all these things, make it higher fidelity, which is bad in terms of optimizing. But there's something to check if you're having stability problems, is you can usually increase your physics time step. We usually run all of our games at 100 hertz, which is kind of bad for optimization. And then in terms of local sliders, the easy thing to change for stability purposes is your mass distribution. You want to make sure it's reasonably appropriate. Like if you had a ragdoll where everything was 1 kilogram, or whatever the units are, that would not make as much sense. If you want the heavier, bigger objects to be much, much heavier, well, obviously. And then as you go farther out on the hierarchy, you want lower and lower mass. And then drag is your #1 factor to fix stability problems, is increase the drag. And of course, then your game will feel floaty. You'll end up with these implicit maximum velocities. But if you're having problems with things jittering or exploding, just start increasing drag until the game feels more sluggish, and then try to figure out how to balance between the two. And we did this a lot in Raptor Safari, is that when the context changed enough that things became very, like when you're picking up a Raptor, we increased the Jeep's mass a little bit to make it easier to tow the Raptor, and then we drastically lower its center of gravity. So I would recommend doing this in your game. If you hit a boost in your car racing game and the car flips over too easily, while you're boosting, increase the drag and then turn the drag back down. The physics system is very tolerant to these real-time changes. You can add a collider, remove a collider, you can change mass, drag, everything on the fly, and you should definitely do it if you're having problems. Or my car feels great, but when I'm in the air, the car feels too floaty. Well, if the wheels aren't touching the ground and you're in the air, just lower drag a little bit so allow it to spin. Or if you're in a car that's highly, highly dampened and you crash, you probably want to kill all dampening so the car has a very satisfying tumble. You should think a lot about how to tune per state in your game. And then any kind of parent-child sort of ragdoll relationship, try to keep the mass much, much higher at the parent, and then as you go out towards the extremities, you want to lower their masses. The problem with parent-child relationships are the strength of a joint is dependent on the masses in the relationship. So if if your torso is 100 and your arm is 1, and you're towing something based on the arm, that arm has very little power on that joint. So it'll basically tear the arm off, and then you'll get this weird physics jittering problem. So the way to fix this is just more drag, avoid deep hierarchies. We lowered the chain count in Raptor Safari just by 2 or 3 chains because it just became more unstable. And then the configurable joint has a projection mode, which is best thought of as snap. So if a joint gets too far out from where it should be, it'll actually just move it back. And if you have this set to every object in your hierarchy, then one object snapping back might cause another object to snap, and then it gets even worse. So only put that on one object in your hierarchy. So on Raptor Safari, snap is set to, I think, the first chain on the Jeep, or maybe the last chain on the ball, so that something will snap back if it starts to move too far. But they won't all be like snap and kind of fight each other. And then the easy way out is just to make your joints breakable. There is a callback on joint break, so your game code can know, okay, well, something broke, I should probably handle it. But if it's really easy to get chains and other joints to pull apart, just make them breakable. So let me quick show something I did over a game jam event that is kind of like a really, really extreme parent-child depth, if I can find it. So this was initially an experiment in something else entirely, but I ended up just kind of going down the path of how many children could I get onto this hierarchy. And the answer in physics is if you do things well and you constantly adjust your mass distribution and your sort of drag distribution, is you can put a couple hundred objects on there without much trouble. So this is a little squid thing. Turn off gizmos. So when I hit T, I get another joint. So it turns out that I can actually hit T a whole lot of times. And every time I add a joint, I'm rebalancing the mass distribution. And I'm also changing the transparency so you can see that the tail is much more transparent. So the objects at the head of this little sperm squid thing are much heavier than the objects behind. So I'm still hitting T the whole time I've been talking. So if I turn around, and the segments are actually really, really small, and they start to freak out a little bit at the end. If you just kind of stop, you'll see that it's cascading with these weird little snaps. But for a couple hours of work, this actually isn't that bad, and it's probably like workable for a production game. Like you could make a game out of this and rely on the fact that it wouldn't just randomly, oh, there it goes. So this is what happened when joints start to pull apart. But the amazing thing is if you can tolerate that, like if your game can tolerate that somehow, if you get back into a more close state, it'll stop. So I mean, this is probably, I don't know, 200 rigid bodies times 4. So it is possible to create very deep hierarchies that are stable. And that's a little bit too deep. And there's the transform rotation is no longer valid, haunting us again. So that's just a little bit on stability. And finally, I'm going to talk a little bit about optimization. There's not a whole lot to say about optimization. So this is the order that I would look at in tuning things. Is the first thing to do is if you have bad performance is to lower your time step. And this is the first thing you should do because if you have a lot of code that isn't taking into account time.delta time, which you usually don't in fixed update because you assume it's going to run 100 times a second or 50 times a second. Then if you change your physics time step and you're applying forces in your game, those forces, if you lower your time step, those forces will feel much, much more strong because a force sort of is over the next 10 physics updates or 100 physics updates. And if there's fewer updates, there's going to be more force. So if you have a very carefully balanced game on, this much force will fire my cannonball, the exact amount that I want, and you lower the time step, then you have to readjust all your forces. So do that first. The next thing is to audit your colliders. Use basic colliders as much as possible. You can have multiple basic colliders for one rigid body. You don't need to rely on mesh colliders for very complex shapes. Just put a bunch of boxes together. By default, this should be okay, but when a rigid body is below a certain speed, it becomes optimized by physics in a very efficient manner. And if those bodies don't actually go to sleep, then you're going to have a bunch of stuff that's active and checking for collisions more than it should be. You can visualize that in the editor with some sort of gizmo. If you have a bunch of ray casts, you should ignore as many layers as possible. You should try to ignore any kind of mesh collider, especially if it's not a convex mesh collider. If it's just a huge concave mesh collider, just try to ignore it and only care about hitting the objects that you really want to hit. We tried to do this in Jetpack Brontosaurus on the next point and didn't succeed so well because we didn't spend a whole lot of time adjusting it. But there's a function in physics just to have two colliders ignore each other. And if you build a manager on top of that, you can say, I am of type enemy. And then you can have other enemies ignore all enemies. So you can have more physical objects because an object in the game might only be colliding with maybe 10 other objects in the player group and not colliding with all of the other enemy objects, for instance. Just don't use kinematic if you can avoid it. It's actually a little bit expensive. And then it's kind of obvious, but just reduce whatever count you have. Try to get away with fewer projectiles, fewer enemies spawned. And I think things to watch out for. Avoid mesh colliders wherever possible. Convex mesh colliders don't appear to be that expensive, and you need them if you want a cylinder or any other basic shape that's not actually exposed from Unity. Joe, please fix that. There you are. Do not move a static collider without a rigid body. It actually causes physics to update some sort of internal tree that keeps track of the collisions. And then if you're putting game logic in fixed update, try to avoid that, especially if your time step is faster than your graphics time step. And lastly, iPhone in physics, it's basically the same thing taken to an extreme. We found that you can get by with about 2 ragdolls, maybe 3 ragdolls, and maybe a dozen colliders in the same scene. But just be scarce. Use box colliders where possible. Sphere collider is the cheapest. Box collider is the most expensive of the basic colliders, and cylinder is kind of in between, or capsule, I guess. And then character controllers are a native physics type, but they do a lot of ray casting, so try to avoid them. And learning resources. So right now it's a blank web page, but we will be launching technology.blurs.com where we will post a lot of our snippets. And we're also, I'm very active on the Unity forums. You can get a hold of me sometimes in my IRC, or you can just email me directly. But the obvious places to learn are the documentation is great. There's a lot of example projects. There's a really old example project with like a physics playground. I don't know if it's still online. And failing that, there's my contact information. Or you can just do matthew@blurst.com. So any questions about any of this? I don't know how much time I have. Yes?
Yeah, how do you create your collision primitives? Do you have some way of creating those in the Arch solution you use?
I didn't quite catch that.
I mean, do you create, I mean, if you're using Max, for instance, do you create collision primitives in Max?
Oh. The actual primitives are only in Unity. So you would add a box collider component type. And if you're doing any kind of mesh colliders, yeah, we just put them in Maya. And it's worth noting that if you have an environment that you need a mesh collider, it's very often worth it to make a simplified collision mesh that's not rendered, but it's just used for collision. Like if you have a really ornate column, you probably don't need to model all of it. Yes?
You mentioned in one of the last panel, do not do static collider.
Yeah.
No idea what you're talking about.
If you have a static collider, like if you're modeling an environment, a static collider is a game object with a collider component but no rigid body component, basically for world collision. And apparently if you move those, it forces PhysX to update some sort of internal tree keeping track of where all of the static colliders are, and that's expensive. So if you have like basically it's for any time you wanted to control an object. So if you had a Pong game and you wanted the paddle just to be a collider that was player controlled and you're moving the paddle back and forth, it's better to do it as a kinematic body than a static collider that's moved by you. Because every time you move it, it forces PhysX to ignore all the optimization it's done. I believe that's correct. We only learned that recently. Yes?
Do you know why the iterations in the PhysX is limited to 100 when I'm thinking it's 255 for the SDK?
That would be a Joe question. The physics iterations, why it's limited to 100 when it could be 255? Like the solver iteration count? Oh, apparently it is. Oh, it's worth noting that we actually changed that on the fly for Splume. So when the Splume levels are built, we actually dramatically increase time step, dramatically increase the solver iteration count, fire a bunch of balls upwards, and then kill all the balls that are below a certain point. Because we didn't want to have a separate logic to build a Splume level that would set all the joints up properly. We just wanted to fire a bunch of balls upwards, let our game logic create all those joints, and then prune it. And we did that by jacking up the time step, so it's like 10 times game speed, increasing solver iteration count. And then when it's done, it's basically like 20 seconds of gameplay in half of a second. So that's another weird physics hack that we did. Yes?
Do you think it's possible to do a Mario Kart sort of vehicle behavior while using physics raycast-based vehicle?
Yeah. I think you could get by with very arcade-style physics, but without doing like pure game logic. I think you could just dampen things very heavily and then get by with like a raycast car doing the actual work on it.
So you think that by tweaking, because using FOSS
Yeah.
program as well as base, and these are healthy number of settings. And so what you're saying is that probably by setting up, by tweaking and tweaking and tweaking, you can get this kind of behavior emerging.
Yeah. So the question was for posterity, could you get like a Mario Kart style simplified racing physics out of like a deeper raycast car? And I think you could tune it so that it would become very, very simplified. And even on the rigid body, you would probably just want to increase drag values there too, so that it isn't very mobile. It would feel sort of fixed. But yeah, you should be able to tune the forest system, which is sort of our system too. You should be able to tune that to model very realistic cars, probably not super realistic cars, like you wouldn't want to be playing any of like the F1 sort of racer sims with it, but you should be able to get a wide range of car behavior out of it.